Hey, I'm Mike and welcome to Need It Make It. Finally, the time has come to test each of these very different 3D printed connections. We're going to put every one of the connections into our new test apparatus to see how well they perform. So, stick around. First off, we're going to need something to put these parts into, so I will create a fairly simple and modular-ish testing setup using some salvage wood by cutting it and then jointing the blanks. I can then plane the parts to final thickness. And do a little bit of layout for the drilling of the parts, and then of course a bit of assembly as well with some wood glue. I've also created the pins from a length of steel rod by machining them on my recently restored metal lathe using the collet chuck shown in the previous video. The idea with this design is that we can use a basic crane type scale and apply the load easily from below. The material I'm going to be using for testing today is PETG carbon fiber, and that is identical to the material that we used in the previous connection videos. It's easy to print, it stays really flat, it's also fairly stiff, and I like that it doesn't smell up my shop. It also happens to look pretty nice. PETG carbon fiber won't have nearly as good layer adhesion as basic PETG, so we might see that coming into play here. I'll be using a 0.2 millimeter layer height for all of the prints, so I will have 6 walls, 12 tops, 12 bottoms, and a fairly dense 30% gyroid infill. I'm also using a 0.4 millimeter nozzle for all of these prints. Hopefully there will be 1 or 2 clear winners from these tests, and we can follow up with some more testing as well with different materials, more or less walls, different nozzle size, really anything that you guys are interested in seeing. Each of these connections we will be testing today appeared in a previous video, and I will have links up above there if you haven't already seen them. We will have a no connection at all, and this will hopefully act as a benchmark. We have a simple lap joint with screws and heat set inserts. We have the tapered sliding dovetail connection. We have the Echol lock. We also have the drop lock. Then we have the sine wave. And lastly, this one appeared quite a few videos ago. This is the under-squinted stop blade scarf joint. Each of these parts was printed so the layer lines are running vertically in the test setup. And to make sure that this is as fair a test as possible, I've modified the orientation of the connections to accommodate that. As usual, all of these are assembled dry. There is no adhesive being used here. For the test setup, we have this frame with these 19 millimeter diameter holes spaced at 50 millimeters apart. Hopefully these holes will allow the test rig to be added onto for different test setups in the future. We'll also be able to move or change the lever position around as needed. Into this jig, we can insert the lever arm using this steel pin, and I will add 2 more pins which support both ends of the 3D prints. I'll also add a custom pin into the lever as well. Next, we can feed the test piece through the frame and through this vibrant custom pressure plate, which is made from 100% solid ABS glass fiber with 2 8mm steel rods inserted into it, which not only look pretty cool, but it does a better job of evenly distributing the load compared to a contact area with a single rod. This part is designed so that the crane scale U-bolt fits into it perfectly as well. We can then connect the crane scale to the lever using these links of chain. And since the weight of the lever and technically all the parts aside from the test piece itself will apply a load, I can at least raise the arm, turn on the scale to zero it out, and then I can let the lever go to account for most of the load applied below the scale. To make sure that I don't need to work as hard in this video and I can avoid grunting and veins popping out of my head this time, the lever will multiply any force that we add at the end. So I can take this bag of sand that's exactly 1 pound, and then we should see about 5.5 pounds or 2.5 kilograms on the scale. What we'll do is insert a printed connection. We'll load up the weights incrementally, and then we can compare deflection on this scale. And we can also take these to the breaking point as well. That is, if we can. The more deflection we have, the less rigid the connection is, which could lead to failing sooner. I'm quite happy with most of these connections, but my favorite connections are the undersquinted stop blade scarf joint. This one was designed to be self-centering thanks to the use of the Surfaces tool in Fusion. And the other connection I really like is the Echol lock. Now, whether they'll actually perform well compared to the others, I have no idea, but I'm really looking forward to finding out. Before we get to the test, please subscribe if you haven't already. My goal is always to make new and interesting content for you. And if you like this topic, hit the notification bell as well so you know when the next video is released. Okay, we are finally ready. Let's go ahead and get some parts into this thing and see what happens. So I have all of the bags of sand here. There are 10 bags, and if that isn't enough, I have this, which weighs 5 pounds or 2.26 kilograms, and I can swap these out, and then I can continue to add them as needed. I have a block of foam just in case I don't happen to catch this in time as it comes down. The cross section of these parts is 25 millimeters tall by 20 millimeters thick. For the first test, we'll do the sliding tapered dovetail connection. That is all of the bags of sand, so I'm going to swap it out. It is not enough still. The joint is still together. I'm just loading this back up and I'm noticing that it really has failed already. It's permanently deformed, but it hasn't broken, so we'll take it to the breaking point. For the next test, we have the drop lock. Next up, we have the screw lap connection. Next up, we have the Echol lock. Next up, we have the sine wave. Next up, we have the under-squinted stop splayed scarf joint. Now last up, we have the continuous piece. So we'll put this in there, see if I can break it. I don't think I'm going to be able to use the sand. I think I'm going to have to do this by hand. Okay, I'm going to put another clamp on this. Holy cow. Holy cow. So let's take a look at the results. What we have here is the amount of deflection at incremental loading points. So we have 10 kilograms, and that is in blue, which is 22 pounds. We have the red, and that's 20 kilograms, 44 pounds, and the orange or yellow, 30 kilograms, 66 pounds. I don't want to go into detail about every one. I want to have a first place, a second place, and a last place as well. So of course we have our benchmark. Next place, which is first place, we had sine wave. Second place, we had the under squinted. And last place, we have the drop lock, which is just barely in last place. For the next chart, we have max deflection and max load. Max deflection on its own really isn't that useful. We'll take a look at max load here. So our benchmark far exceeded the rest of them. Next, we had under squinted. And then second place, we had sine wave. Last place, we had drop lock. And the last chart that we are looking at here is the amount of deflection per kilogram. And again, I have blue, red, and yellow. And then I have the green, which is the max failure point. Next place, we have sine wave. Next after that, under squinted, and drop lock came in last place. If we want to put a third place, it would be the Echol lock. So what exactly is the takeaway from all of this testing? Well, if you can print continuous, it is far superior to any of the connections. But if you don't have an alternative, one of these two options is a pretty good choice. And both of these are self-centering, and that is thanks to using the loft command within the Surfaces tab in Fusion 360. And also because of that, they are constantly changing direction within the 3D print, so there is no one defined weak point in either of these prints. In this case, I was able to get this one right back together. It didn't even break. It just deformed enough to have the joint come apart. Though it did just about break me when it flew out of the test rig. Whoa. Just about in my direction, wow. And in the case of the sine wave, this one came apart at the heat set insert, which means there should be a way to improve this quite a bit more. Now, when we compare the worst performer versus one of the best performers, it's not difficult to see why there's such a big difference. With the drop lock, we have these individual fingers, and each one on their own is fairly flexible and much more prone to breaking. When we take a look at the sine wave, we have each side having only one finger, if you want to call it that, and it's going to take far more force to deform those fingers enough to cause the connection to come apart. So when it comes to connections in 3D printing that do not use any adhesive, it is important to have the parts as substantial as possible. And that holds true as well for this connection, which has these individual small interlocking dovetail fingers. This smallest one let go first, which eventually led to its demise. If you're interested in using or testing any of these yourself, I will have the STL files, I will have step files and Fusion 360 files available for any of you, and there will be a link down there below. So next week we're going to have the torsion testing, and we should be able to put all of the stats together, so I hope to see you on that video. This test rig is also just a prototype. I'd love to improve this quite a bit more so that I don't need to add weights. So if you have a good idea that you think would work really well, let me know, and it could make it into the version 2 or even version 3 of this rig. Thank you to each of my patrons for helping to support this channel and making these videos possible. And of course, if you want to help support this channel as well, there is a link down there below. Take care, and I hope to see you on the next one. But if you don't have an alternative, one of these two options is